Paris, 1898. I want to transport you back to the turn of the century for a minute.
You're setting the scene.
Yeah, exactly. So the Eiffel Tower is, what, only 9 years old at this point? And physics as a field is feeling pretty good about itself.
Very good about itself. The height of deterministic arrogance, really.
Right, because we have Newton's laws, we have thermodynamics. We basically feel like if we just measure things accurately enough, we can predict literally anything in the universe.
Which is a comforting thought.
It is. But in a study in Paris, there's this mathematician named Jacques Hadamard, and he is sitting at his desk, basically about to ruin everyone's party.
He really did.
So I want you to picture a billiard table. But this isn't the flat green felt table you'd find in a pub. Hadamard is imagining a theoretical surface.
Right, a surface of negative curvature.
Yeah.
And it helps to visualize this carefully because everything we discuss in this deep dive rests on this specific shape.
Okay, so how should we picture it?
Imagine a saddle.
Wow.
Or, actually even better, imagine a bull's head.
A bull's head. Okay.
Yeah, so you have that saddle shape in the middle, right where the forehead would be. And then you have these two long horns curving away, stretching off to infinity.
Got it. So the key feature here is that negative curvature.
Exactly. On a normal flat table, the surface is neutral. If you have a ball, it curves in on itself. That's positive curvature.
Right.
But on the bull's head, the surface curves away from itself in different directions. It opens up.
Opens up, okay. Now, Hadamard performs a mental experiment on this shape. He imagines taking a billiard ball and rolling it along this bull's head.
Assuming perfect conditions, right?
Perfect conditions. No friction, perfect motion. The ball just follows a path, what mathematicians call a geodesic. The straightest possible line you can draw on a curved surface.
And this is where the trouble begins.
This is where the universe breaks. So Hadamard imagines taking two balls, he places them on this bowl-shaped surface, and he places them infinitesimally close together.
How close?
I mean, practically on top of each other. Maybe they differ in position by, like, the width of a single atom. And he rolls them in the exact same direction.
Right, and if you did this on a flat table, those balls would just roll parallel to each other forever.
Sure.
And if you did it on a sphere, like the Earth, they would eventually converge. They'd meet at the pole.
But on Hadamard's bowl.
They diverge. And they don't just drift apart slowly either.
Yeah.
Because of that negative curvature, that saddle shape, the distance between them doubles.
It doubles.
And then it doubles again and doubles again.
It's exponential separation.
Precisely. Exponential. If they start 1 millimeter apart, very soon they're 2 millimeters, then 4, then 8. And very quickly, one ball shoots off down the left horn and the other shoots off down the right horn.
Total opposite directions.
Their futures become completely opposite, yes.
And what Hadamard proved here, sitting there with a pen and paper 65 years before the very first computer weather simulation, mind you, was a revelation that honestly should have kept every scientist up at night.
It's profound.
He proved that you can know the laws of physics perfectly. You can know the exact shape of the table. You can be a Newtonian determinist down to your bones.
And yet you still cannot predict the outcome.
Exactly.
This is the critical distinction we need to make right at the start of this deep dive.
Right.
Determinism does not guarantee predictability.
Right.
The ball perfectly obeys the laws of motion. It doesn't have free will. It isn't just randomly jumping around. But because of the geometry of the space it's rolling through, the slightest unmeasurable difference in where you drop it explodes into a completely different future.
Explodes. And that is the topic of today's deep dive. We are tackling the shape of chaos.
This is a big one. I mean, it's one of the most misunderstood concepts in science.
It really is. And we have a massive stack of sources today. We're going through papers by Ruel, Takens, Edler-Renz, Robert May, medical journals on heart fibrillation, and historical math papers going all the way back to Hadamard.
It's a heavy stack.
Yeah. And our mission today is very specific. We are going to prove to you that chaos is not randomness.
Correct. Randomness is just a mess. It has no structure whatsoever. Chaos has a shape.
A shape. We're going to show that while the future of a chaotic system, the specific path it takes, is unpredictable, the statistics of that system are mathematically determined.
They're rigid.
Rigid and reliable. We are going to find the order hidden inside the disorder.
And to do that, we really have to look at the geometry.
Yeah.
We're going to understand that the chaos isn't just something happening to the system. The chaos is the shape the system lives on.
Okay, so let's unpack this. We started with Hadamard in 1898, but the story really goes mainstream with the weather.
It does.
Yeah.
But actually, before we get to Ed Lorenz and his famous weather machine, we have to bridge the gap a little. We have to give a quick nod to James Clerk Maxwell.
Maxwell, like the electromagnetism
A
guy.
very same. Back in 1876, he actually hinted at this whole thing.
Really?
Yeah, he was looking at gas dynamics, and he noticed that in certain physical systems, there were points where, as he put it, small causes produced great effects.
Oh, wow.
So he saw the crack in the armor of that Victorian determinism we were talking about.
He realized that if you had a system where a tiny nudge could flip the outcome entirely, prediction became impossible.
Exactly. Why? Because you can never measure the present perfectly? There's always an error bar. Always.
Right, and if your error is microscopic, but the system amplifies microscopic errors, your prediction just falls apart.
Completely falls apart. But the thing is, Maxwell didn't have the math to prove this was generic. He thought maybe these was just rare, unstable points.
Like balancing a pencil on its tip or something?
Exactly like that. Rare and highly specific. He couldn't prove that this sensitivity was the rule rather than the exception.
And that had to wait for Ed Lorenz in 1963, and of course the invention of the computer.
Yes, the man, the myth, the butterfly.
Let's set the scene here. It's the early 60s. Lorenz is a meteorologist at MIT.
And he's working with a Royal McBee LGP30 computer.
I love the names of these old machines.
Oh, this thing is a beast. It's the size of a desk. It uses vacuum tubes, and it literally sounds like a jet engine taking off. And it's incredibly slow by modern standards. I mean, thousands of times slower than the phone in your pocket.
Right. And he's running a simulation of atmospheric convection on this thing, basically just how hot air rises and cold air sinks.
Right. He distilled the weather down to 3 simple differential equations.
Okay.
Now, for those who haven't done calculus in a while, a differential equation just describes a rate of change. It tells you how fast the wind is speeding up or slowing down based on where it is right now.
Got it. So he has this system running. It's chugging away, printing out numbers on a roll of paper that represent the weather. And the legend goes he wanted to rerun a forecast to see what happened further out in time.
He wanted to double-check a sequence, yeah. So he had a printout from a previous run. And to save time, instead of starting the whole simulation from 0, he decided to start it right in the middle.
Makes sense.
So he typed in the numbers from the printout, the temperature, the pressure, the wind speed, to initialize the machine.
He hits run, goes to get a cup of coffee down the hall, comes back an hour later, and what does he find?
Well, he expects the new run to match the old run perfectly.
Yeah.
Obviously. It's the same equations, the exact same math.
Right.
But he finds that the new simulation has diverged completely. It started out tracking the old one, but then it drifted, and then it swung wild. By the end, it was describing a totally different weather system. One run said sunny, the other run said blizzard.
And his first thought was that the computer was broken, right? Like a vacuum tube blew out?
That was his very first thought. But then he looked closer at the number he actually typed in.
Okay.
The computer worked with 6 decimal places internally. So inside the machine, a number was stored as, say, 0.506127.
Right, 6 places.
But the printout, to save paper space on the roll, the printout only showed 3 decimal places. It just showed 0.506.
So he typed in 0.506. He totally ignored the 0.000127.
He did. And that tiny difference, less than 1 part in 1,000, was enough. The errors grew exponentially, exactly like the balls on Hadamard's bull. They doubled and doubled until the 2 futures looked absolutely nothing alike.
And this is the famous butterfly effect, but I actually want to stop right here because pop culture has absolutely ruined this term.
Oh, it really has.
People think it means everything is connected. You know, a butterfly flaps its wings in Brazil, and that physically causes a tornado in Texas.
Right.
It's become this almost mystical trope about destiny and how every tiny action matters. But mathematically, that's not really the point Lorenz was making, is it?
No, and I'm really glad you flagged that. We need to be extremely precise here. The butterfly isn't the cause. The butterfly is the geometry.
Explain that. What do you mean the butterfly is the geometry?
So when Lorenz plotted the behavior of his system, he took those 3 variables and plotted them as a single point moving around in 3D space. He didn't get a random scribble. He got a specific shape.
The double spiral shape. It looks like a mask or, yeah, a butterfly. 2 wings connected right in the middle.
Exactly. That shape is the attractor. And this is the single most important concept we need to land in Act 1. You absolutely have to distinguish between the trajectory and the attractor.
Okay, let's break that down slowly. The trajectory is the path the weather takes day by day.
Right. The trajectory is the motion. It's the specific sequence of states. Today it's sunny, tomorrow it rains, Wednesday it's windy. In a chaotic system like Lorenz's equations, the trajectory is unstable.
Unstable meaning sensitive.
Highly sensitive to initial conditions. If you change the starting temperature by a billionth of a degree, the trajectory eventually goes somewhere completely different.
So the trajectory is the unpredictable part. It's the billiard ball rolling on the bull's head.
Correct. But the attractor is the set of all possible trajectories. It is the geometric shape that the system is completely confined to.
Confined to.
Yes. No matter where you start the simulation, the trajectory eventually settles onto this butterfly shape. It orbits the left wing for a while, then it flips over to the right wing, spirals there for a bit, flips back.
But it never repeats itself.
It never repeats the exact same path, no. But it never, ever leaves the butterfly.
Okay, so the trajectory is transient and unpredictable, but the attractor is permanent and stable.
Exactly. Think of it this way. The weather changes, but the climate is the attractor. The specific path the wind takes is the trajectory, and it's lost to chaos. We can't predict it past a week or two.
Right.
But the range of things the wind can do, the limits, the patterns, the overall shape of those possibilities is rigid. It's the butterfly.
So when we titled this deep dive, The Shape of Chaos, we are literally talking about this geometric object that traps the system.
Yes. Chaos isn't formless. It is rigidly confined to a strange attractor.
But this brings us to the machinery under the hood, right? Like, why does it form that specific shape? Why doesn't the system just fly off to infinity or eventually settle down to a single boring point?
Right, that's the big question.
We need to talk about the load-bearing math here. We need to talk about the rate of chaos.
Yes, we do.
Yeah.
We need to talk about Lyapunov exponents.
Okay, let's take a deep breath. Lyapunov exponents. I mean, that sounds terrifying.
It sounds like a grad school nightmare, I know. But it's actually very intuitive if we just use physical analogies.
Okay, hit me.
A Lyapunov exponent is simply a measure of how fast nearby points in the system separate or converge. Remember Hadamard's billiard balls?
Yeah.
And the rate at which they doubled their distance?
The doubling rate, sure.
That rate is the positive Lyapunov exponent. It just measures the stretching.
Okay, stretching. But a system like the weather or the Lorentz equations has multiple dimensions, right? So it has multiple exponents.
Correct. The Lorentz system has 3 dimensions. So it has 3 Lyapunov exponents. And to understand what they do, I want you to imagine a small blob of state space.
State space.
Yeah. Imagine a little cube of Play-Doh floating in the air. This cube represents a tight bundle of possible weather conditions that are all very, very similar to each other.
Got it. I have a little cube of Play-Doh possibilities. What happens to it as time moves forward?
Well, the positive exponent stretches it. It's exactly like pulling taffy. It takes 2 points that are close together inside that cube and physically rips them apart.
Okay.
This is the source of the unpredictability. It amplifies those microscopic differences into macroscopic ones.
That's the chaos. That's the butterfly effect in action, stretching the taffy.
That's the chaos. But here is the problem. If you only had stretching, the system would just explode.
Right, the numbers would just get bigger and bigger.
Exactly. The weather would get hotter and hotter or windier and windier until the atmosphere literally stripped off the planet. The taffy would stretch to infinity. And we know that doesn't happen. The system is bounded.
So there has to be a counterbalance to the stretching.
There is. The negative exponent. The negative exponent is the squeezing. It compresses the state space.
Squeezing.
Yeah, think of it like a hydraulic press. While the positive exponent is stretching the taffy out long, the negative exponent is aggressively crushing it flat.
Wow. And in the Lorentz system, which one of those wins?
This is a really cool part. We can cite the specific numbers straight from the Lorentz equations.
Let's hear them.
The positive exponent, the stretching, is about plus 0.91. That's how fast information is being created, how fast uncertainty grows.
Plus 0.91, okay.
The negative exponent, it's around minus 14.57.
Whoa, wait a minute. So the crushing is way stronger than the stretching.
16 times stronger. The system is being massively compressed.
But wait, if it's being crushed that hard, why doesn't it just shrink down to a single dot? Why doesn't the weather just stop completely?
Because of the stretching. It's a literal tug of war. You have this blob of possibilities. It gets stretched out long in one direction by the 0.91, but simultaneously crushed flat in another by the 14.57.
Okay.
And then, and this is the magic of the whole thing, because the overall system is bounded, It has to fold back on itself.
Stretch and fold, like kneading dough.
Exactly. Stretch, fold, squeeze. Stretch, fold, squeeze. And you do that infinitely many times, and what do you get?
Well, let's think. If I take a sheet of dough, stretch it, and fold it over once, I get 2 layers, then 4, then 8.
Keep going. Infinite times. You don't get a solid volume because it's been crushed completely flat by that minus 14.57 exponent.
Right.
But you also don't get a simple 2D surface either because it's been folded over itself infinite times.
Oh, you get a fractal.
You get a fractal. You get an object that has a fractional dimension. And this is exactly where the Kaplan-Yorke formula comes in.
Yes, the Kaplan-Yorke formula. This is our tier 1 math, right? This is the bedrock of the episode.
Rock solid tier 1. James Kaplan and Jim Yorke derived a formula that allows you to calculate the literal dimension of the attractor based solely on those exponents.
Based entirely on the battle between the stretching and the squeezing.
Yes. So dynamics writes geometry.
Dynamics writes geometry. That's the phrase.
The dynamics, the exact rates of stretching and folding, dictate the final geometry of the object. It's a ratio. You compare the stretching rate to the squeezing rate.
Let's walk through that ratio for the listener.
Roughly speaking, the Kaplan-Yorke formula asks, does the squeezing overpower the stretching? If the squeezing is infinitely strong, you just get a line or a point, dimension 1 or 0. If the stretching is stronger, the object puffs out. But for the Lorentz attractor, when you plug in those exact numbers, the plus 0.91 and minus 14.57, the formula spits out a dimension of approximately 2.06.
2.06. Okay, hold on. I need to wrap my head around this. I know what 2D is. It's a flat sheet of paper.
Right.
And I know what 3D is. It's a solid box. What on earth is 2.06D?
It's a geometric object that is slightly more than a surface.
Slightly more.
Yeah. It looks like a pair of wings, which are surfaces. They look 2D. But if you were to zoom in with a microscope on the edge of the wing, you wouldn't see a single flat line.
What would you see?
You see layers, infinite layers, packed incredibly close together. That thickness of infinite layers gives it that extra 0.06 of a dimension.
So the butterfly isn't a solid object at all. It's an infinite stack of sheets, infinitely close together, created by that endless folding process.
That is the shape of chaos. It's not a mess. It's a highly structured, fractal object with a specific dimension, calculated directly from the tug-of-war between predictability and unpredictability.
That is actually beautiful. Okay, so we have the shape. We know the weather is trapped on this 2.06-dimensional butterfly.
Yes.
But as a listener, I'm sitting here thinking, great, the weather has a shape, but I still don't know if I need an umbrella next Tuesday.
Right, and that's the rub. We've established that you can't predict the specific trajectory. The ball is lost.
Right.
But here's where it gets really interesting. This brings us to the third act of our mathematical foundation, the SRB measure.
SRB, Sinai, Ruel, and Bowen.
3 absolute titans of mathematical physics. They asked a fundamental question. If a system is chaotic and trajectories are jumping all over the place, how do we predict anything at all?
And the answer lies in the statistics.
Correct. The SRB measure is essentially the unique probability distribution that describes what you actually see in a physical chaotic system.
Okay, probability distribution is a bit abstract for me. Give me something I can visualize.
Imagine a busy hotel lobby.
Okay.
And imagine the guests in the lobby are the trajectories. They're running around like crazy, checking in, checking out, running to the elevator, going to the restaurant.
Pure chaos.
Right. If you try to track one specific guest, let's call him Mr. Smith, it's impossible. He's unpredictable.
So Mr. Smith is the weather.
Mr. Smith is the weather. But suppose you take a camera and you take a long exposure photograph of that lobby. You leave the shutter open for a full hour. What do you see on the photo?
I just see a blur.
You see a blur, but it's not a uniform blur, is it?
No, I guess not.
The blur is darker near the check-in desk because people stand there longer. It's darker near the elevators. It's lighter in the corners where nobody ever goes.
Okay, I see.
That blur map is the SRB measure.
Oh. So even though I have absolutely no idea where Mr. Smith is at any given second, I know with 100% certainty that 80% of the guests spend their time near the elevators.
Exactly. The SRB measure tells you the density of the chaos. And here is the kicker. The trajectory, Mr. Smith, is completely unstable. But the SRB measure, the blur map, is rock solid. It never changes.
This perfectly connects to another analogy I saw in the notes for this section, the card shuffling.
Yes. I love this one. This is great for visualizing the geometry we just talked about. Imagine a deck of cards. You shuffle it.
Okay.
In the direction of the shuffle, the cards are being completely randomized. That's the unstable direction, the stretching. You have absolutely no idea where the ace of spades ended up.
That's the unpredictable future.
But look at the side of the deck. The cards are stacked perfectly on top of each other. The total height of the deck hasn't changed. The distribution of plastic and air is completely rigid.
Wow.
The SRB measure basically says the system is smooth and random along the direction of the shuffle, but fractal and rigid along the direction of the stack.
So connecting this back to the big picture of the weather, we can't predict the trajectory beyond a week or so because of the positive Lyapunov exponent, the stretching.
Correct.
But we can predict the climate.
Precisely. We can perfectly predict the average temperature, the variance in rainfall, the probability of extreme events over 100 years.
Yeah.
Because those are properties of the attractor, not the trajectory.
Yeah.
And the attractor is beautifully described by the SRB measure.
This is the ergodic theory payoff. We trade certainty about the exact moment for certainty about the long-term statistics.
And that trade is exactly what makes science possible in a chaotic world. If chaos didn't have this rigid statistical backbone, if it didn't have an SRB measure, we couldn't study anything complex.
We'd be blind.
We couldn't do climate science. We couldn't study turbulence. We'd literally just be looking at noise.
So just to give a quick Act 1 summary for you listening, chaos isn't random. It's generated by a deterministic process of stretching and folding.
Right.
The stretching and folding creates a strange attractor with a specific, measurable fractal dimension like our 2.06 butterfly. And living on that attractor is the SRB measure, which gives us rock-solid statistics even when individual predictions fail completely.
That is the foundation.
Yeah.
That is the Tier 1 math. And now we have to see where this math actually lives in the real world.
Right. Because so far, we're just talking about atmospheric physics and billiard balls. But the realization that came in the 1970s was that this math doesn't just apply to fluids or gases. It applies to life.
It applies to literally everything.
So let's move to Act 2, chaos in the wild. And we have to start with a physicist who walked into the field of ecology and completely overturned the apple cart, Robert May.
Robert May, 1976. This is such a classic story of interdisciplinary disruption.
What was the state of ecology at the time?
Well, ecologists at the time were using these very complex computer models to try and understand population fluctuations. Trying to figure out why the number of fish in a pond or rabbits in a field goes up and down over the years. And they assumed that if the population was bouncing around erratically on the graph, it must be because of the environment.
Like bad weather, or a fox entering the hen house, or a sudden disease, external noise.
Right. The fundamental assumption was complexity in the output must come from complexity in the input.
Makes intuitive sense.
If the graph looks messy, it's because the world is messy. But May said, hang on a second. He looked at the simplest possible equation for population growth, the logistic map.
This is a very famous equation. Let me read it out. X sub n plus 1 equals r times x sub n times 1 minus x sub n.
It sounds fancy when you say it out loud, but it's incredibly simple. You have a population, x, and you have a growth rate, r. The population next year simply depends on the population this year, multiplied by that growth rate.
That makes total sense. Rabbits have babies. The more rabbits you have, the more babies you get.
Exactly. But there's a catch.
Yeah.
The 1 minus x term.
Right. What is that?
That's the starvation factor. If the population gets too high, resources run out. There's not enough grass, and the population crashes.
Oh, I see.
So you have a feedback loop. Growth pushing the numbers up, starvation pushing the numbers down.
And what did May find when he started turning up the growth rate in this simple equation?
He found the route to chaos. And this is something you can easily visualize. When the growth rate is low, let's say R is 2, the population just settles down to a steady number. Equilibrium. Boring.
The classic balance of nature.
Exactly. But as you turn the knob up, as the creatures reproduce faster, say R is 3, the equilibrium becomes unstable.
Unstable how?
Suddenly, the population splits. It starts oscillating between two distinct values. You get a high year, then a low year. High year, low year, a 2-cycle.
Okay, that's a predictable oscillation. Boom, bust, boom, bust.
But turn the knob a tiny bit more, that 2-cycle splits again. Now you have a 4-cycle. High, medium, low, very low. And repeat.
Whoa.
Turn it just a little more. 8-cycle. 16-cycle.
It's cascading.
It's a period doubling cascade. And the bifurcations, these splits, happen faster and faster. The window for each cycle gets smaller and smaller until suddenly you hit a critical number.
And then what?
The period becomes infinite. The population never repeats. It bounces around wildly, looking completely, utterly random.
But it's not random. It's still just that exact same simple equation.
It's fully deterministic. There is no external noise at all. There are no foxes. There's no weather. The chaos is generated entirely internally by the dynamics of the population itself.
And here's where it gets really weird,
Mm-hmm.
because this leads us to Feigenbaum universality.
Yes, Mitchell Feigenbaum, a physicist at Los Alamos. He looked at this cascade that May found, and he actually measured the rate at which these doublings happen.
Like how fast you go from a 2-cycle to a 4-cycle.
Exactly. He found a specific number, a mathematical ratio, which is approximately 4.669.
4.669. Okay, so that's the magic number for rabbit populations.
That's exactly what he thought. But then he looked at a completely different equation, sine waves. He found the same cascade and the same exact number, 4.669.
Wait,
Then he looked at fluid flow, same number.
hang on, pause. Are you telling me that a dripping tap, which is simple physics, and a population of rabbits, which is extremely complex biology, break down into chaos using the exact same number?
To the decimal point.
That makes zero sense. Rabbits aren't water droplets. Rabbits have livers and instincts and DNA. Water is just water.
This is exactly why it shocked the physics world to its core. It implies that there is a fundamental way that order breaks down into chaos.
It's universal.
It doesn't matter if you are a fish, a dripping faucet, or a convection current in liquid helium. If you have a hump in your function, a feedback loop that pushes back when things get too high, you will follow this exact road and you will pass the mile markers at exactly the ratio of 4.669.
That is just mind-blowing. It suggests that chaos isn't just a breakdown of a system, it's a universal structure underlying reality.
It's deep structure. It's a law of nature as fundamental as pi.
But I think we should add a quick caveat here. We're calling this Tier 1 math. Feigenbaum's work is completely solid. But when applied directly to ecology, there's still some debate, right?
Correct. We definitely have to mention Alan Hastings and his review here.
Right.
While the math itself is rock solid and
Yeah.
may absolutely change the paradigm, proving that a specific wild population is chaotic versus just noisy is incredibly hard.
Because real data is messy.
Exactly. You can't just isolate the rabbit variable in the real world.
So May didn't necessarily prove that all of nature is chaotic.
No. But he proved that irregularity doesn't require external noise. He entirely shifted the burden of proof. Before May, if you saw a messy graph, you just assumed it was a messy world. After May, you had to ask, is this noise or is this internal chaos?
Okay, so ecology gave us the mechanism. Now let's look inside the human body. Let's talk about the heart.
This is such a fascinating application. For a long, long time, the medical assumption was simple. Regularity is health. You want a perfectly steady heartbeat. Metronomic. Chaos is disease.
I mean, that seems intuitive. If my heart starts skipping beats, I'm going to be worried.
Right, but the data suggests something much more nuanced. Let's look at ventricular fibrillation.
The thing that kills you during a heart attack.
Exactly. The heart muscle stops beating in sync and just starts quivering like a bag of worms.
Is that chaos?
Early models by Weiss and Garfinkel suggested yes. They modeled the electrical waves traveling through the heart tissue.
Okay.
In a healthy heart, the electrical wave sweeps across smoothly. In fibrillation, the wave breaks. It curls into a spiral. Then that spiral breaks into multiple spirals.
That sounds familiar.
It's a spatiotemporal cascade. It's very similar to what we saw in the logistic map, but it's happening in space as well as time.
So fibrillation is a chaotic state.
In these in vitro models, yes. And this led to a truly brilliant idea called OGY control, named after Ott, Grbogi, and Yorke.
Chaos control.
Right. Think back to the butterfly effect. Sensitive dependence on initial conditions?
The taffy stretching.
Usually we think of that as a bad thing, right? It prevents prediction. But Garfinkel and his team realized it could actually be a profoundly good thing.
How can extreme sensitivity be good?
If the system is sensitive, that means you don't need a sledgehammer to change it. You can use a tiny nudge.
Oh, I see where this is going.
If you time it exactly right, when a trajectory is near a specific point on the attractor, you can apply a microscopic electrical perturbation and literally push the heart back into a stable rhythm.
So instead of a massive defibrillator that shocks you with 1,000 volts, resetting the whole system with a scream, you could potentially pace the heart with a whisper.
Exactly. pacing with a whisper, by using the geometry of the chaos against itself. If you know the exact shape of the attractor, you know exactly where to push to move the ball where you want it.
That is incredible. But now we have to make a very clear transition. We're moving from the heart tissue models, which are tier 1 physics-based models, to clinical reality.
Right. We need to be very careful here. We're entering tier 2 territory. This is where the science is active, it's contested, and it's fascinating.
We're talking about heart rate variability, or HRV.
Yes. It turns out that a perfectly regular heartbeat metronomic regularity is actually often a sign of pathology. It's highly associated with heart failure or aging.
Wait, really? A super steady heart is bad? That sounds totally backward.
It implies the system has lost its flexibility. Think about it. A healthy heart is constantly adjusting, speeding up a tiny bit when you inhale, slowing down when you exhale, reacting instantly to hormones. It fluctuates.
Right, it adapts.
And when you mathematically analyze those fluctuations, they look fractal. They have a 1/Fron noise signature. They look exactly like a strange attractor.
So the working hypothesis is healthy chaos.
The idea is that health is a state of high complexity. A healthy system has a high-dimensional attractor. It can access many, many states. It's adaptable.
And disease.
Disease is a collapse of that complexity. A failing heart gets stuck in a low-dimensional rut. Either it's too periodic, like a monotone, or it's too random, like fibrillation. Health is poised perfectly in the middle, in the chaotic regime.
That's a really powerful idea. Health as dynamic complexity.
It is, but remember, the actual clinical utility is still being worked out. We can measure HRV on our smartwatches, but we aren't quite at the point of chaos controlling a human heart in the ER yet. That's exactly why it's tier 2.
Okay, moving further up the body, we're going to the brain, and I'm going to put a big flashing red light here for you listening. Warning, danger zone.
High alert.
We are entering the realm of neuroscience and complexity theory, tier 2. Active, aggressive debate. This is where the scientists start throwing chalk at each other in seminars.
It really is. Let's start with a very controversial but fascinating claim from 1985 by A. Babloyance. She analyzed EEG data brain waves during sleep and during epileptic seizures.
And what did she find?
She claimed to find a dimension inversion. We usually think of a seizure as a storm, right? Chaotic, messy, out of control.
Yeah, that's the perception.
But her analysis suggested that during deep sleep, the brain is actually high-dimensional. It's chaotic. It's doing a million different things. But during a seizure, the dimension completely collapses.
The seizure is simpler.
Mathematically, yes. A seizure is hypersynchronous. Millions of neurons firing in perfect lockstep.
Wow.
It's a low-dimensional limit cycle. It's not chaos. It's pathologically rigid order. The beautiful complexity of the brain collapses into a simple, loud, repeating pattern.
So again, health is chaotic complexity. Pathology is ordered simplicity. It perfectly matches the heart story.
It matches it perfectly. But, and here comes the immediate critique, we have to introduce James Thieler, 1986.
A gotcha.
A massive gotcha. Thieler looked at these precise dimension calculations where Babloyan said, oh, the dimension is exactly 4.05, and he said, wait a minute. Proving chaos from a short string of biological data is incredibly dangerous.
Why is it dangerous?
Because of something called colored noise.
Okay, explain colored noise.
Sure. So white noise is totally random, zero correlation between data points. But pink noise or brown noise is correlated.
Correlative meaning?
It means that if the value is high right now, it's very likely to be high a millisecond from now. It has a memory. It wanders.
Like a drunk person walking home.
Exactly like that. A drunkard's walk. It has structure. And if you run the chaos dimension algorithm on that noise, if you feed it random correlated noise, the algorithm can be completely tricked.
Really?
Yes. It will spit out a number. It will confidently say, oh, look, a dimension of 3.5. But there is no strained attractor at all. It's literally just noise.
Spurious dimensions.
Exactly. So Thieler argued that just because you calculate a dimension on an EEG, it doesn't mean the chaos is real. You might just be looking at correlated noise. This was a giant wet blanket on the whole field. It forced everyone to be much, much more careful.
So where do we stand now? Is the brain chaotic or not?
Well, the consensus has evolved. We've mostly moved away from trying to calculate a specific number, like dimension 4. Instead, the leading theory now is criticality, or the edge of chaos.
The edge of chaos.
Researchers like Beggs and Plenz have shown that neuronal activity forms avalanches.
Avalanches. Like snow.
Actually, more like a sand pile. Imagine dropping grains of sand one by one onto a pile. Most grains do absolutely nothing. Some cause a little tiny slide. But occasionally, one single grain causes the whole pile to catastrophically collapse.
And the brain does this.
The brain does this. The firing of neurons follows a power law distribution. This is the exact mathematical fingerprint of a system sitting exactly at the critical point, the phase transition between rigid order and total chaos.
But why would the brain want to sit right there? That sounds inherently dangerous.
It's the absolute sweet spot for information transfer. If the brain were too ordered, subcritical signals would just die out, they'd get stuck. But if it were too chaotic, supercritical signals would explode like epilepsy. Overwhelming noise everywhere. The edge of chaos is the only place where information can travel long distances across the brain without dying or exploding.
So the brain surfs the boundary. It uses the chaos to stay flexible, but it uses the order to stay coherent.
That's the current modern synthesis.
Yeah.
And it actually connects beautifully back to Stuart Kauffman's work on gene networks.
Oh, let's talk about Kauffman.
He proposed that cell types, like being a liver cell, or a skin cell, or a neuron, are essentially attractors in the gene regulatory network.
Oh, I love that. So the entire genome is the dynamical system.
And the specific cell type is the stable basin of attraction. Once a developing cell falls into the liver attractor, it stays there.
Wow.
It's completely stable against small perturbations.
Right.
But if you shock it hard enough, you might theoretically push it out of that basin and into a different one, maybe a cancer cell attractor.
This unifies so much. We see the exact same geometry attractors, basins, stability versus instability, appearing in the sky, in the heart, in the brain, and all the way down in our genes.
And that leads us perfectly to the synthesis.
Act 3. Let's connect the dots here. We started with Jacques Hadamard and a billiard ball on a bull's head. We ended with the human brain surfing the edge of chaos. What is the actual through line for you listening?
The through line is the chain we built slowly in Act 1. Dynamics writes geometry, geometry writes statistics.
Let's restate that, because that is the bumper sticker for this deep dive.
The dynamics, the Lyapunov exponents, the constant stretching and folding create the physical shape, the strange attractor.
Right.
That attractor has a specific measurable fractal dimension. And living right on that attractor is the SRB measure, which dictates the long-term statistical behavior.
And life. Where does life fit into this?
Life doesn't fight chaos. That's the biggest mistake we make. We always think biology tries to be perfectly ordered. It doesn't. Life utilizes the geometry of chaos.
That's the key insight.
Think about it. Biological systems absolutely need to be reliable. You need your heart to beat every single day. But they also need to be adaptable. You need to be able to instantly run from a tiger.
Right.
If they were purely ordered like limit cycles, they'd be rigid robots, completely unable to adapt to a changing environment. If they were purely random, they'd be dead. Chaos, specifically the SRB measure, gives you the best of both worlds.
You get the statistical reliability, the climate, so you can maintain your bodily homeostasis, but you get the trajectory instability, the weather, so you can react instantly to a predator or a completely new idea.
Exactly. The SRB measure is essentially the memory of the system. In a chaotic system, individual trajectories are forgotten instantly. The sensitive dependence just wipes the slate clean constantly.
Right.
But the structure, the attractor itself, remains. Biological reliability comes from the stability of the attractor, not the stability of the path.
It's structure without repetition.
Beautifully put.
Yeah.
There's infinite variety, safely contained within a finite shape.
And this really calls back to our previous deep dives on fractal dimensions, doesn't it? Like measuring coastlines or fissure information. The fractal dimension isn't just a math trick. It's a direct measure of the system's functional complexity.
Exactly.
So we've covered a massive amount of ground today. Let's do a quick confidence check. You're the expert here. Score the science we've talked about.
Okay. Let's start with Tier 1, rock solid. This includes ergodic theory, Lyapunov exponents, the existence of strange attractors, the Kaplan-Yorke formula,
The heavy math.
the heavy math. It also includes the logistic map and the period doubling cascade and Feigenbaum universality.
Yeah.
This is pure mathematical bedrock. It is proven, it's tested, it's simulated, and it's observed in real physics experiments like Libchaber's liquid helium.
And Tier 2.
Tier 2 is the pattern recognition side in biology.
Right.
The application of these math concepts to clinical HRV, the edge of chaos hypothesis in the brain, and those specific dimension calculations of biological data.
Because of the noise.
Because of the noise. The core concepts are sound. We know for a fact the brain uses nonlinear dynamics. But the specific measurements in noisy, real-world biological systems are highly subject to critique, like Thaler's critique. We know the brain uses these dynamics, but proving a specific numerical dimension is still a bit of a dark art.
Fair enough. Let's hit the listener with 3 main takeaways to put in their pocket.
Takeaway 1. Chaos has a shape. It's not a mess. It is a strange attractor with a specific fractal dimension. When you hear the word chaos, don't think random. Think fractal geometry.
Takeaway 2.
Predictability is purely statistical. You absolutely cannot predict the butterfly's path, the trajectory, but you can completely predict the climate, the SRB measure. We basically trade certainty of the future for certainty of the distribution.
And takeaway 3.
Universality. The exact same math, the exact same Feigenbaum constant, 4.66, governs the dripping faucet, the human heart, the population of fish, and the convection of the atmosphere. There is a deep universal architecture to how systems behave when they become highly complex.
And that brings us right back to where we started. Paris, 1898.
Jacques Hadamard.
He drops that theoretical billiard ball on the bull's head. It rolls, it hits a patch of negative curvature, it diverges.
The path is totally lost.
The future is unknowable.
But the horn is still there.
That's the final thought I want to leave you with. The ball chooses a path, and that exact choice is entirely unpredictable. But the horn, the geometry, the attractor was there before the ball was ever dropped. The shape of chaos precedes the motion.
The shape is the reality. The motion is just the shadow.
Thanks for diving in with us today.
Always a pleasure.
See you next time.